All right, welcome back. This time, we're going to talk about large-scale training in SageMaker. But before we get started, hit the like button, subscribe, or share with anyone taking the AWS Machine Learning Associate exam. So, training massive models, foundation models, and LLMs with billions of parameters requires specialized infrastructure and optimization techniques. SageMaker provides an integrated suite addressing these needs: training optimization tools, resilience and recovery mechanisms, distributed training frameworks, and hardware acceleration. So first we'll go with SageMaker Training Compiler. So Training Compiler accelerated model training by compiling models into hardware-optimized GPU instructions, achieving up to 50% speed up on supported instances. This will be the ML.P, P3, P4, G4, G5. It integrated into AWS's deep learning containers for PyTorch with XLA. So enable it in PyTorch estimator using the training compiler config. However, it's incompatible with SageMaker distributed training libraries. AWS has deprecated training compiler with no further updates, though it may still appear on certification exams. So, warm pools. Warm pools avoid provisioning overhead by reusing training infrastructure across jobs. This benefits repeated training workflows, fine-tuning and hyperparameter searches, where startup latency and data reload times reduce efficiency. Specify a keep alive period in your training job's resource configuration to maintain VMs and cache data on persistent volumes during warm periods. This requires a service limit increase through AWS Support Center. You're billed for idle warm time, but this costs less than full reprovisioning for every iteration. The trade-off favors workflows and frequent training cycles. Checkpointing. So checkpointing enables resumable training through automatic state synchronization. It saves training state snapshots to S3 at intervals, synchronizing them between opt/ml/checkpoints and your specified S3 path. This supports resuming long jobs after interruption and debugging progress in large-scale training. Configure checkpointing in your SDK with a checkpoint flag and a checkpoint local path flag. These parameters are useful. You could also do it through the console, which was shown earlier during your training job creation under checkpoint configuration. Health checks. Okay, so automatic health checks validate instance and GPU health via NSCCL before training starts. They replace failed nodes automatically and restart entire jobs on service errors like SageMaker internal crashes. This prevents wasted training costs from hardware faults during long jobs. Health checks are enabled by default on ML.P, P4, and P3 instances. Okay. So, distributed training. SageMaker offers two main approaches for training single models across multiple machines. Data parallelism, which is it distributes different data slices to each instance. Gradients average across nodes using all reduce. Enable in PyTorch estimator through the distribution's parameters. This builds on AWS's custom collective library with all reduce, all gather collectives, and offloading GPU communications to CPU for optimization. Model parallelism splits the model across different GPUs when it can't fit in a single device memory. This becomes essential for LLMs exceeding 1 billion parameters. Memory saving comes from optimizer, state sharding, activation, checkpointing, and activation offloading to CPU. Enable this in your estimator configuration. The current version 2 of SageMaker deep learning container supports this only with PyTorch. So some alternative frameworks. Oh, that's more on parallelism. Okay, so some small alternative frameworks. All right, so beyond SageMaker's implementations, you can use open source alternatives. PyTorch DDP is native to PyTorch, but requires manual setup. Horovod supports TensorFlow. PyTorch and MXNet are also useful. DeepSpeed from Microsoft focuses on large LLMs. ML.Prune or MPL Run, and Torch Run provide command line parallel training runners. Most require P3, P4, or TRN1 instances. Elastic Fabric Adapter, right? EFA enables low latency, high throughput networking for tightly coupled distributed GPU training. This specialized network adapter delivers performance similar to on-prem HPC clusters. It works with NCCL for optimized GPU communications. You can use the P4 or P5 EC2s for GPUs with EFA enabled. Your container must include NCCL and the appropriate plugin with the environment variable set to EFA. All right. Let's see. Do we have mics? Okay, so mics minimize communication scale is AWS's architectural pattern combining SageMaker sharded parallelism, elastic fabric adapter, ultra clusters of A100 GPUs on P4 instances, and fast shared storage via Amazon FSx for Lustre. This enables training models exceeding 1 trillion parameters like GPT scale LLMs across thousands of GPUs. The key hardware includes P4 instances with 8x A100 GPUs and 400 gigabytes per second networking. FSx for Lustre providing petabyte scale high IOPS storage, and EFA for low latency GPU to GPU networking. So the costs. So large scale training costs accumulate quickly. Warm pools charge for idle GPU times between jobs. Distributed training multiplies instance times, durations, times instance type rates. EFA requires expensive specialized instances. Checkpointing adds S3 storage and synchronization times. Mike's ultra clusters involve customized pricing, massive EC2 fleets, right? So in the P4 instances cost approximately $32 per hour. So multiply that by 1,000 nodes and training becomes millions per month at scale. So we're not going to do this. Just when I listed that, we're not going to touch this because you have to configure a lot of things that are very similar to what we've already done, but you're doing it at scale with your S3s, your instances, and you're going to scale this out with similar hyperparameters. All right. However, for the exam, remember these essentials. When questions ask about training models exceeding single GPU memory, optimizing distributed training performance, or recovering from training interruptions, understanding these large-scale training technologies will help you to the right answer. So we're going to get going, but before we do, hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. Thank you, and have a good day.